we mentioned before that more than 90% of industrial chemistry depends on catalysis. And more than that, 90% of catalysis depends on heterogeneous catalysis. This means more than 80% of industrial chemistry depends on heterogeneous catalysis. Now we can. So what are the advantages of heterogeneous catalysis? We talked about the difference between homogeneous and heterogeneous, and we will talk again later, inshallah. But let's briefly mention some of the advantages of heterogeneous catalysis. First of all, it increases the reaction rate. Of course, it's increased the reaction rate. If it doesn't increase the reaction rate, this means it is not a catalyst. Okay? It increases the reaction rate, yes. But if we compare with homogeneous catalysis, we may say other words. It's a relative expression. Selective, of course, it's selective. All catalysis should be selective. But which is higher than which? It's selective, okay. Reusability. Yes, it is. This is the main advantage of heterogeneous catalysis: to be separated and reused again, recyclability. And these are some keys, some key characteristics that it has surface area. Yes, it has surface area, but let me ask you a very simple question: which one has more surface area, the homogeneous catalyst or heterogeneous catalyst? The surface area in homogeneous catalysis is a kind of virtual meaning. That means it is not a solid, but we are talking about the contact area between reactants and the catalyst. Which is higher than which? Excuse me? Heterogeneous catalysis? No, it's homogeneous catalysis, because we mentioned that the contact between reactants and the catalyst in homogeneous catalysis is much bigger than heterogeneous catalysis. So the rate and the activity of homogeneous catalysis is higher than heterogeneous catalysis. Why? Because in heterogeneous catalysis, only surface sites are working. The reactants see or absorb on only the surface sites. But in case of homogeneous catalysis, all the material is working, okay? Porosity, this is very nice character which increases surface area, and also we use it in the for the selectivity of some reactions, as we will mention in other lecture, inshallah. Stability, of course, it is stable. These are main advantages of heterogeneous catalysis. Now let's talk about very interesting and very popular and very nice reaction. The mechanism of this reaction is very important to understand and to be able to monitor this reaction, and also to be able to modify and increase its activity. Of course, for photocatalysis, it means photo and catalysis. Photo and catalysis. This means you have two terms. The first term is photo, the second term is catalysis. Photo means you are using photons or light, whether it is UV light or visible light. Okay? These photons are going to the reactant or the catalyst. It activates or change some changes in the electrons of these reactants or catalyst. Okay. After these changes, product comes. This product is radical, which will initiate the reaction. Again, light comes to the surface, changes happens to the material, radicals will be produced. These radicals will initiate the reaction. Okay, let's go here. That of course we have just mentioned catalysis is the acceleration of catalyst, and this is light, and photocatalysis is the combination between two expressions. And this is photocatalysis is one of the promising techniques. Of course, it has been used since 17th. And photocatalysis is the acceleration of a chemical reaction by either direct irradiation or by irradiation of a catalyst that is in turn lowers the activation energy for the primary reaction to occur. Photocatalysis, of course, it happens in some materials. The most famous one, the most famous material which is used in photocatalysis is titanium. And the titanium is a semiconductor, and titanium is the most promising material, yes, but we sometimes it needs to change or to modify or to increase the activity of titanium, and that happened really and readily in past. If you imagine this is your material, or it has a semiconductor, it has two bands, which are the valency band and the conduction band. If you imagine that you have, of course, the difference between these two bands is the energy gap. If you have an electron in valency band, of course, if you give this electron an amount of energy, it will go to conduction band like this. Of course, this energy should be quantized. I mean, this energy should be limited and fixed number or fixed amount of energy. It shouldn't be less, but it may be higher than this energy. This required the energy between energy gap. It's like I think you already know what I mean. The excitation of electron in the valence band to conduction band will cause the presence of hole. This hole is positive in valence band, whereas the electron will be in conduction band. Now, in conduction band, yes, but it is negative sign or negative charge. Now you have two parts, two opposite charge parts, electron and hole. Now you have two possibilities to happen. The first one is electron will return back again to the hole, and this is called electron hole recombination. Okay? This is the first possibility. And this possibility will be higher if this distance between energy gap, this distance between the two levels or two bands is small. And if recombination will happen, that means your reaction will proceed and will go on or will be inhibited. If recombination will happen, this means your reaction will be inhibited because you return back to 0 point. What did you gain from just excitation and return back? What did you gain? Nothing. Just return back, and the energy you was gained from this electron will be emitted again. That's all. But the other possibility is so the first scenario, or the other scenario is the reduction. This electron will make reduction for oxygen to produce oxygen radical, and in the same time oxidation of water by the hole to form hydroxyl radical. Okay, this is the second possibility. Here is written first possibility. The second possibility is the electron hole recombination. So those are the two scenarios or two possibilities you have. The second scenario, which is electron hole recombination, will be great if the energy gap is small, and will not happen at all if the energy gap will be very high. But if this is good to make the energy gap will be very high. Make it very high. this will make good reaction or not. You will forbid electron hole recombination, and all will go without returning back. Will it be good for your reaction or not? It is still not good for your reaction. Why? Because you will need much energy, higher energy to excite these electrons. It's useless. So the most important or the brightest or the most useful scenario is to make this band gap is intermediate, to forbid this energy electron hole recombination, and also to use little amount of energy. Not little, just intermediate amount of energy. And how it goes. So we talked about the two scenarios. Of course, there are of course, many of you has studied many reactions of photo degradation of dyes, and you use the titania and may use the you made promotion of titania with different metals or different metal oxides, or you supported titania on other supports, and you had better data. Okay, of course, this is a story that we just mentioned now, that this produces electron hole, and this electron hole will be divided like this conduction band and valency band. This is how it goes. This is very simple, of course. We have two possibilities. The first one is you use your beaker or your reactor. Beaker is a reactor. Okay? The beaker is a reactor. Don't feel that the word reactor is very big word, but still the beaker is a reactor. When you use your test tube, you add HCl plus NaOH. This is a reactor. Okay. This beaker, which is a reactor, has our catalyst, which is platinum 25. Platinum 25 titanium is a type of titania, which is a mixture of anatase and rutile, and this is cover nanoparticles. All of them are here, and xenon lamp will be there, and will emit UV to this reactor, and the stirrer will continue. This is a very simple experiment of photo degradation. You add your dye and you add your catalyst, and you make adsorption at the first for some time until adsorption will be completed, and the reaction after that, the degradation will be due to the reaction. After some time, you take some a sample as from time to time at different time intervals to trace or follow the reaction, as we mentioned yesterday. If you remember, we mentioned some data about degradation and UV data. Do you remember this data? Several peaks at the same chart, if you remember. And this is another type of this is another system of photocatalysis. It is double jacket tube. The inside tube has the lamp, which is xenon lamp from up there. It is similar one is inside, and then the jacket. But the inside tube should be in quartz, and the outside may be in Pyrex, no problem. Why quartz? Because quartz will not absorb UV irradiation. And this is thermocouple to this one is thermocouple to measure the temperature. And of course, there is a stirrer, and this is a system. Okay, these are I just brought these to for you to imagine how it goes. And these are the importance of photocatalysis. It has several applications in industry, several applications as in food industry, and in degradation of dyes, and in the removal of wastes from water and the air, and in preparation of some type of glasses, and several applications of photocatalysis. And I think we can say thank you very much for your attention, and it was nice to meet you today. Thank you.
So the first session is over. Please, anybody has any question or any doubt? Yes, please.
Actually, I didn't understand how we got the auto radical during the reduction part.
Excuse me again, I didn't.
Can you explain again how we got the auto radical during the reduction?
How?
How we got auto radical?
Auto radical? You mean the reaction to form radicals? Okay, shall you? I finished, okay? Okay.